Okay, friends, we shall now move from Delhi to Bangalore. Our next speaker is Siva Athreya. He will explain about Brownian motion on random trees or real trees.
Real trees. So the title is very broad. I'll try and focus on more questions than results. I'll try and give a brief introduction to our trees. It's required. More approaches. The goal that I'll state, I think, is too hard to achieve. So there's plenty of motivation for the subject, but yes, we'll see. So since I'm being recorded for this talk, I thought I'll do my first karma. So why I'm here is for this visit. So if you look at the New York Times bestseller list, my book with Sundar is right there on that page, next to Yogi Berra's book of Driving Mr. Fudge. And you all by know now how we make our book a bestseller. So at the counter, when I said I don't want my bag, the person said, there's a very good book inside the bag, you should take it. So you go to New York Times, it has a bestseller list, right? So. New York Times bestseller? Yeah. How did you do this? It's there, yeah, it was there yesterday. It may not be there today, but it's there yesterday. So I'll begin with a very simple example, at least in probability. I'm not sure how familiar audiences outside probability are. So it's a basic invariance principle. If you have done an undergraduate probability class, you would have seen the central limit theorem. The functional version of that. So if I take a random walk, or just take a particle on the integer lattice, the jump size is given by x, and x is a random quantity. So at each step I jump by x, so it can be positive or negative. Then I interpolate on the real line between these points. So I get a path x. And then this path, if I scale by root n in space and I shrink time, then that converges to what's called Brownian motion. So I'll be a little bit vague what I mean by law. I'll ignore it. I won't define Brownian motion, so at least in this context. So the basic picture is something like this. So this is like on the left-hand side is a bunch of random walks. So it's not quite clear but on the right-hand side is Brownian motion. What I want to sort of motivate as a point of thought is that, so random walk is on this space, 1 over root n z with the corresponding metric. I can think of it as it stays at each site for time 1 over n, and then jumps around. Okay, so. And this process with some holding time converges to Brownian motion on the real line with the Euclidean metric. So, it's the same thing, I'm just saying it differently. So as my talk continues, it will be clear why I'm phrasing it like this. But so it's just norm doesn't come in. I'm just saying it's a metric space, 1 over root n z with the Euclidean metric. I'll phrase it in a second. Why the. So here's a more general version of this. So if you have done probability, I don't think anybody would have, or a course on weak convergence. So example 0, I have stated a bit imprecisely, but the philosophy is correct. So the classical central limit theorem or going to Brownian motion is phrased on the integer lattice. But let's say I do the following. I have my rationals. It's a countable set. I take any enumeration. I take a set of finite sets that sort of grow up to the national sets. On these finite sets, I have a random walk that sort of moves around. inversely proportional to the distance between the points. So with those holding times. Now, as I get bigger and bigger, I'll get more and more points. So I'll start jumping quicker and bigger between points that are closer. And is this another way of getting Brownian motions? This is why I motivated the last line in the previous slide, where there's a metric involved and then there's a holding time involved. And then so of course, I present the question. I've called it example 0. So it is true, but not in the. It's not precisely written up there, but the spirit is correct. So you can do this. You can take rationals, take random walk rationals, and then. But you can't take random walk on the entire rational because then you have to define some other measure. But if you take finite sets, you do the same thing. Of course, you have to. The little trick, you have to complete the space in the end, and that's not that's in the converge part of the whole. But question 1 is kind of what I want to focus on. So I have a sequence of metric spaces, perhaps discrete, so discrete points with some metric Rn. I have some random walk on the metric space. Now, there are various notions of metric spaces converging to other metric spaces. If this happens, can I say my random walk converges weakly to Brownian motion on the big metric? So before that, there's also an obvious question. You need to know what do you think is a Brownian motion on the big object VR. So on the real line, we know we have a standard object. On RD, we have a standard object. In general, we don't know. Yeah. No, I have phrased it very generally, so I have not. I'm asking, yeah. So these are questions like I said, these are goals that I have not formulated precisely, but these are examples to think about, for example. But whatever things I'll consider, they will be fairly unique. So the real motivation for such questions came to me 6 years back. David Aldous asked me this question. So let's see. So you have so let's forget the title of the slide. Let's look at the graph there. So I have, let's say, the natural numbers as one graph as the backbone. At each point in natural numbers, I put a random finite tree. Okay, how to generate random finite tree is you put a Galton Watson tree. That's going to be finite almost surely. So you put a finite random tree at every point, and that's your graph tau. Okay, so graph tau is one backbone and finitely many Galton Watson trees at each point. So you have finite trees with the same distribution and independent at each point. So it's known probabilistically that this graph tau is the same in law, or the random graph tau is same in law as a critical Galton Watson tree condition to survive. So that's a representation that's known for some time. So Keston showed in '76 that if you take random walk on this graph tau, then it's a subdiffusive behavior. So for example, I don't know if you notice my first slide, I scaled my random walk by root n. But here the scaling is 1/3, so it's different. So you have to be careful when rescaling the path of random walk. So yeah.
By random walk, you mean go to any neighbor equal probability?
Yeah, that's right. Yeah, just take a graph and just jump equal probability. Yeah, as of now, yeah. So each time step, you just pick a neighbor and then walk around. That's the random walk. And distance from rho at time k, you take the maximum time n. It's 1/3, so it's tight. So it's not diffusive scaling. So it's a different scaling. So of course now there's sort of further developments on this. This was shown in what's called the annealed regime, where he averages over all the random environments. But now it's been shown omega by omega as well. So question long time was that what is the scaling limit of this object tau? So again, what I mean by scaling limit is that you should again go back to 1 over root n z, sort of going to the real line you have an understanding of that. Is there a similar scaling of this? So I rescale the tree edges in some way. I do some rescaling. Do I get a different object? So that's been answered. So each of these finite Galton Watson trees, if you rescale, they go to an object called the continuum random tree. I'll explain that tree in a second. So David Alder asked me, first thing was that, can you construct Brownian motion on such limiting trees? Because that would give you a diffusion with a different scaling rather than the usual scaling. And anomalously slow diffusions are very useful tool in some problems in statistical physics. So, but what happens is that when the I'll explain it. Yeah, I'll explain in the next slide. Yeah, not next slide, maybe 2 more slides. So the formal idea is the following. So 1 over root n z goes to the real line, right? So okay, so in some fashion. So okay, so here if you want to scale, you do is like you take edge lengths, let's say 1 over n.
No, I guess he's asking even what is mean to say 1 over root and then
Yeah. So you can take a, let's say you take.
No, in standard random walk, you go step plus 1 minus 1. Right? In this template, suppose you go plus 1 minus 1. Right.
That's right.
Right. Jump sides. Maybe I'm jumping the gun a little bit. It is a Brownian motion. Are you expecting to be a Brownian motion in the limit?
Yeah. So I'll discuss what it one more. Yeah. I'll discuss it as well.
So rephrase, what you mean is that you take the adjacency matrix of lattice, and then you're putting once, you scale it to
Yeah, that's one way looking at it. That's one way looking at it. Yeah. That may not be the ideal way of looking at it in general, but yeah, that's one way. Yeah, that's fine. That's fine. Yeah. So what turns out is that the limiting objects are a class of objects called real trees. So let me discuss them and discuss real trees for them. These are called R trees. They were discovered by Andres. They were discussed by paper in Andres Dress some time back, late 80s. So they are path connected, zero hyperbolic metric spaces. Okay, so take a metric space. It's path connected. So any 2 points in the metric space, you can walk along a path inside a metric space. What does zero hyperbolic mean? It's got no loops. That's one. There's a unique path between 2 points. That's clear. What's more important is between any 3 points, there's a unique branch point in the middle. Okay, so if I take any 3 points on a metric space, this, and this, there's a unique branch point. That's called zero hyperbolic. So no, not necessarily. Not degree C. I take any 3 points. There's a unique branch point that connects the 3 points. That's what zero hyperbolic is. But just think of it, think of a metric space, that's a tree. That means it's a graph with no loops. But it can be very general, so it need not be discrete. It can be sort of the real line is, for example, the first example, the real line is the simplest R tree. RD is not an R tree for dimensions bigger than 1, because take any 2 points, there are several paths that connect them. That's not an R tree. Any regular tree is an R tree. Your average comb is an R tree, of course, it should be a little thin edge. A star is an R tree.
So when you say that any 3 points are connected to unique,
Via a unique branch point, yeah.
doesn't have to be a neighbor, right?
No.
Branch point need not be a neighbor.
That's no. Yeah, no. It's a metric space, so there's no, yeah.
it can be like T.
Yeah. There is a vertex that you can call as, you can fork from there and go to all 3 points. And it can be anything. It can be, you can have an infinite end that keeps on going.
What you just went degree 3 or more.
Yeah, degree 3 or more. Yeah, say I take x, y, z. There is a point C with a path to y, path to x, and path to z. And that's unique. There can't be 2 such points. You can have finite paths that have open ends, like an open interval. You can have closed ends, and so on and so forth. It's any metric space that looks like a tree. That's called a real tree. I don't want to go to the formal definition because it will take me. So these are more interesting examples in probability. They are trees below excursions. So let's see. So if you look at the left-hand side picture of my graph, I have a continuous function that sort of goes up by 1 at each time step and comes down by 1 at each time step in any sort of odd fashion. So here it goes twice up and then comes down once, goes twice up, comes down once. So below any such excursion, I can form a tree. So how do I form that? I go to every local minima, I draw a flat line, and I reach out for the nearest local maxima. Okay. So that's the formal picture. So I go to every local minima, I draw a flat line, I go up vertically to the local maxima. Okay. So out pops the tree. Okay, so. And similarly, from any discrete tree like this, I can construct an excursion on this side up to a certain equivalence. Because the time point here is sort of is a sort of vague picture, but formally this is the idea. Okay, so I take an excursion, I can get a tree below it. I have a tree and get excursion. Up to an equivalence class, this construction is sort of well defined. So now, if I take a simple random walk and I wait for it, the first time it comes to 0, starting from 0, I get what's called a Galton Watson tree. If I take a Brownian excursion, I get what's called a CRT, which is what I meant by rescaling of the other. So you can define it as edge length of the tree itself, or define it in excursions as well. So these are examples of R trees. And the construction you can make rigorous exactly the way I said. Look at every local maxima is a sort of a leaf. Every local minima is a branch point. And this construction can be made rigorous. And these are very interesting trees in probability. And the Brownian contra tree, which I said was a rescale limit of the Galton Watson tree in the 2 slides below, is obtained this way. You take a tree below a Brownian excursion. Yeah.
Your description for that picture of the tree, I don't quite understand why. Is there a non-uniqueness?
Yeah, it's up to equivalence here, to be careful. So, up to equivalence. I can write the equivalence down. So, because like I said, this time point is sort of coming down. Edge length, you can write it down precisely. This is called Harris construction. You can write. I'm not going to do it. So several approaches available in the literature. So now the whole thing is now I want to construct Brownian motions on R trees. That's my goal. That's my sub goal now. And I also want to construct. I want to know how to construct them. And I also want to keep the question in the background of the mind that I have a discrete object, I have a random walk on it, and does that rescale to my Brownian motion? So these two competing sort of questions. So there have been, on metric spaces, there are several sort of constructions of Brownian motion. Most of them have been sort of have been existential in the sense that there is an approximating sequence. You somehow show the sequence is tight. You show the limit point exists. It's unique in some sense, and that you call the limit point as Brownian motion. And the approximating sequences are all random walks, and they sort of. So this has been very active since 80s. Fractal work, serpency carpet. And Kigami 95 sort of was working on analytic networks. So it's a paper in Journal of Functional Analysis. He shows that he calls them objects as dendrites, but dendrites are essentially R trees, are complete R trees. Okay, so the metric space is complete, and it's an R tree. Then it's called dendrites, according to him. He proposes a way in which you can construct an approximating or random walks, like my rational example, which gives you a limiting object, but he's not able to characterize a limiting object. It's an existential proof, and that's what he doesn't call it Brownian motion. He calls it something else. I forget the exact name he gives. Then Kumoga and Sturm on. So you take a metric space. I mean, it's hard to sort of understand when can you construct Brownian motion on it. If it has a specific relationship with the real line or a Euclidean space, you can lift the Brownian motion and put it on there and do something with it. But if it doesn't have an abstract space, to define Brownian motion is you can't construct Laplacian on any metric measure space. You have to sort of believe me on that. So you need to have some sort of volume estimates and doubling estimates. So if you assume those things, then Kumagai and Sturm construct an approximate Laplacian. Again. So you have a discrete finite structure in the metric measure space that goes up to the whole one. And on these discrete ones, they have a discrete Laplacian, and they're able to show there's a limiting one. Okay, so that's one. So that's the analytic work. On the probabilistic side, the CRT has a lot of structure. So like it's below a Brownian excursion. You can use the leaves to construct a leaf measure. And using leaf measure, you can construct a probabilistic diffusion on it. And that's been exploited by Krebs and Crowden. And Steve Evans constructs what's called what he calls the R tree. So the R tree is one in which every point is a branch point. So it's like a very rich R tree. So it's a metric space. It's called the R tree. And then, of course, it's the richest R tree, but there's a definition for it, and I don't want to go there. But this he does, again, because the R tree has a specific structure, he's able to lift the Brownian motion from the real line and put it on the R tree. Okay, so via this map that I didn't describe in the definition of the R tree. But again, all these approaches, these don't give a limiting form. These give a limiting diffusion, but they give a specifics. They use a specific part of the tree, some imprint of the tree. So there wasn't when we came to this project, there wasn't a sort of a generic approach for constructing Brownian motion on any given R tree. So I give you a metric space, I call it R tree. Can you construct Brownian motion for me on it? So, of course, when we started in 2006, so there's several competing approaches, and it's still going on. Croydon has several papers after that. So what we decided to do was we went back to the real line. So there's several ways of constructing Brownian motion in the real line. So one such way is using the Dirichlet form construction. So what's the Dirichlet form? It's a bilinear form that satisfies some characteristics. So let's leave out mu for the time being. So if I define a bilinear form, E of fg as 1/2 Lebesgue measure times f prime g prime. This equality will hold if the functions are in A. Otherwise, the integration by parts formula will give something else. So you take derivatives in L2 lambda, you define this bilinear form. So f prime g prime. Okay. And then the Dirichlet form theory will tell you that if your form is regular, which means the domain is rich enough, there are a lot of functions in the domain, then you can construct a Laplacian, then you construct a semi-group. So the bottom line is Fukushima's book. It's 500 pages, but there's theory underlying there. If you show form is regular, then you can do this whole construction. So we thought that fine, if I take an R tree, can I imitate this construction? Can I take a Dirichlet form? Can I show it's regular? And abstractly get a Laplacian and a H semi-group. And that I will call my Brownian motion. So this is what I'm going to do. And I can show that. So one can show for the real line, I put a measure nu. So regularity, essentially, you show conditions about the domain of the form. See, if the domain is empty, then the form there's nothing to the form, right? So you show the domain is dense in the class of continuous functions of compact support, in the soup norm, and a couple of conditions you have to show.
The quadratic form definition of the Laplace.
That's right. That's what I'm doing right now.
What is regularity?
Yeah. Regularity means the domain is rich enough. Yeah. See, you can define any form you want. Then if there is if the domain has nothing in it, then the form is also meaningless. So for example, that's why my nu comes into play. If you look at my nu, my functions are in L2 nu and in A. But, yeah, I'll tell you. I'm coming to that in a second. Yeah. Functions are L2 nu, but the derivative is in L2 lambda. Okay, so this condition can be orthogonal to each other in many cases. So nu is what's called the speed measure of Brownian motion. So essentially, I'm constructing a diffusion by this construction. So nu defines how fast the Brownian motion is going to go. So if mu is, let's say, a constant multiple wave measure, that means all I'm doing is, if mu is c times dx, then all I'm doing is my diffusion I'm constructing is BCT. So, so where B is standard Brownian motion. So nu indicates what's called a speed measure of Brownian motion. Okay, so for example, like in Rajiv Karandikkar's talk, he had sigma of xs dbs. No, he had a operator with a of xs times the second derivative. So speed measure in that case would be 1 over ax dx. So that would be your nu. So you can ignore nu in the real line case because nu Lebesgue measure itself is radon, so you can replace this by lambda as well. But if you have any radon measure, you can construct on the real line Brownian motion with speed measure nu. So that's what. And it's a diffusion coefficient. So it's not, okay. So why I'm writing in this form is that in many cases on real trees, if you have a length measure, it may not be radon. So we were able to successfully do this. This to appear soon, I guess. So we were able to construct a length measure on any locally compact artery. We were able to construct a gradient, constant gradient on any locally compact artery. And we were able to construct a space A which sort of defines this vanish infinite suitably, which gave you a Brownian motion on TR. Okay, so the techniques are very similar to the real line. Once you have these ingredients, the techniques are similar. You show regularity of the form, which takes a few pages. But once your Dirichlet form is regular, then you have several techniques available from the theory. Like green function, you have capacity, you can get various estimates on heat kernels. Of course, the Dirichlet form theory is abstract. To convert it to probabilist notation takes some time, and then there's always confusion here and there. That's the idea. So what does this do? It gives a unified construction of Brownian motion on any given artery, any locally compact artery. So, for example, the example that I gave you in the beginning, this tau with all these Galton Watson trees on it, it's rescale object itself. You have Brownian motion on it now. That's what's called the Kallenberg tree, by the way. I didn't say that name then. It covers all existing constructions, Gordon Krebs. So I'll come to this line in a second. It provides, very importantly, a very useful tool. We didn't realize it then. The referee pointed out to us that it provides a limiting expression for Kigami's forms. So Kigami had this electrical networks in which this rationals go into the real line example that I had. So you have an approximating sequence and an existential limit. You can show that it's the same form as the previous slide. So this is the form. So Lebesgue measure times gradient is the form. So it now gives a limiting expression for Kigami's form. And once the referee pointed out that this covers other approximating approaches as well. So
Aren't you going to get always a symmetric process here?
that's right, yeah, always symmetric. Nu symmetric, yeah, with respect to nu. And now once you have a limiting form, you can do fun things with it. You can get mixing time bounds. You can recover recurrence transients results. This we knew. Russell Lyons has several papers on random walks on trees, so you can recover them as well. So it's kind of a fun approach. So once you have a limiting form, you can show all these things, then you can do various things with it. So now I have a limiting object now. So now what I want to do now is that I go back to my original question now that I had. I have a discrete sequence of metric spaces, but discrete, I don't know, you can think of what you want. They converge in some sense to VR. Does my random walk on V and Rn converge to nu? Okay, now I don't have to go back to the old approaches because I have a limiting Brownian motion if VR is an R3. So if VR is an R3, I have a limiting Brownian motion. Now I want to understand if random walks converge to that. But then I have to understand what this equality, this quotation means. So that's a theorem that's in preparation. It's almost there. So if you have a metric measure spaces, a sequence, discrete arteries, that converge in what's called the Gromov-Weak topology to another metric measure space, then the nu-n random walk on T and Rn plus a moment condition will go to this Brownian motion. So let's see. So two things I glossed over. See, if I take any random walk on 1 over n on let's say 1 over root n z, if it doesn't have second movement finite, if it jumps very, very far, very, very quickly, then the center limit theorem will not hold and it will not go to Brownian motion. So in my rational example, somehow that was rigged because I took finite sets and I went slowly. So I have to have some moment condition on the walk. So we're writing it down. And this Gromov topology is also, it's not very easy to work with, but it's fairly intuitive. So you embed everything in one big metric space. And in that metric space, you compare the Hausdorff distance between the sequence and the limiting metric space. And the Prohorov metric, metric between the measures. So a natural thing to do, but of course it's very abstract to work with. But this sort of theorem will be now useful to do various things. For example, I can use Keston's theorem on random walks to get a limiting results on Brownian motion. So this is the kind of the future. Once that theorem is finished, then. So I didn't explain the second point. So incipient infinite clusters are interesting objects in percolation. They're discrete objects. They're countable. They're not R trees, but somehow when you rescale them, you get a tree in high dimensions. This is called R. So then the next thing would be to do is that you take any graph, you have a random walk on the graph. If the graph converges in metric measure space, as a metric measure space to a real R tree, to an R tree, can you show that the random walk goes to Brownian motion? And this has implications in several problems in statistical physics. We are not very close to the answer, but reasonably there. So this is another way of, this last line, natural scale, is another way of characterizing Brownian motion is that, so there's in Brownian motion interval, if you start at a point x, you try and see if you hit b before a, it's a linear function in x. So that's called natural scale.
How will you get measures that center of a non-locally?
Yeah, I don't know. Non-local geometry, you have to use this you can't use regularity, you have to use what's called quasi-regular forms you have to show. It's a little bit more work. Okay. That's all I had to say mathematically. So, but I thought I should have some fun at Sundar's expense at the meeting. So that's right. So these are, I just wrote National Archives, but so Sundar and I met way back in '92, so first time. I think he was as young as I was at that time. I think. So you were close to 40 at the time, maybe. I was right now. He was as young as I am right now. You're close to 40, I think. Yeah, you're close to 40, I think, at the time. So '92. So these are exams of me and my classmate at the time, Anuvik Biswas. I just put it down. That's fine. Then. So Sundar, as also is well known for his generous feedback. I don't know if you can see this. Let's see. So there's a big X here. So I don't know if you can. So this you can't see, but I had written the polar identity incorrectly. So. And the question mark was in red. It comes out in black if I rescan. The handwriting is similar. So of course, you should note that the numerator is close to the denominator. So it's one of the standard feedbacks from he was always very generous in the exam, which I have sort of followed in my students. So there are two people who were there with me in '93. So let's see if this works. I don't know. So I called them and I asked them to say something for today. So they both obliged, and they both obliged in their own way. So Anumik also is so they both are very, how do you say? I say nice things about them, but so they're tough and warm people. Yeah. So Anumik has this to say. So you can listen in. It's a wireless, sir. Okay, it's coming, but it's not coming. It's on all, yeah. Okay, it's not coming. Okay, I'll just put my mic there. Just one second.
Shiva called to tell me that I should say something on Sundar's 60th birthday celebration conference. No? What nonsense. Sundar is only 40.
Can't hear it?
Good morning.
I'm trying to do that. Okay, let's see. Good that I finished early.
Good morning, everyone. Yesterday about 2 a.m., Shiva called to tell me that I should say something on Sundar's 60th birthday celebration conference. What nonsense. Sundar is only 40. That was about how old he was in July 1992 when we first met. It has been 2 decades since.
I'll try once more.
Good morning, everyone. Yesterday about 2 a.m., Shiva called to tell me that I should say something on Sundar's 60th birthday celebration conference. What nonsense. Sundar is only 40. That was about how old he was in July 1992 when we first met. It has been 2 decades since. I know that...
Okay, so Uma's a bit louder, yeah, so let's listen to Uma first and then come back to this one.
Hi, Sundar. I can see you're having a quiet celebration. I remember when Vijay and I were doing that apprentice thing with you, you turned 40 and we were not invited to the party. I'm still sulking. Oh well, I don't know if you remember, but one of our earliest conversations was about Lewis Carroll, Cabbages and Kings. We have talked of many things since, things we did not quite anticipate. I'd like to say to you what you once wrote for me. Always keep the faith. Have a wonderful birthday.
Yesterday about 2 a.m., Shiva called to tell me that I should say something on Sundar's 60th birthday celebration conference. What nonsense. Sundar is only 40. That was about how old he was in July 1992 when we first met. It has been 2 decades since. I know that some members of my family still regret that day because he, according to them, lured me into mathematics from quote-unquote more lucrative statistics, and they would be 100% correct. I scanned a copy of my first exam as recollections from that class, and Sundar, if you are listening, I still feel that I deserve more points on that. I just omitted some details. What I remembered from that class, apart from the lectures, is to go up on the board frequently to do homework problems, and after having written just one line, hearing someone yell from behind, "What nonsense!" Anyway, we enjoyed the torture so much that we extended our year to the month of May and June in 1993, and Sundar gleefully complied. Many mathematicians much better than I today would talk about Sundar's accomplishments, but to me he is in the same league as Jones and Popa. I hope he continues this until he is 90 years old. That's the sound of the champagne bottle popping. Happy birthday, Sundar.
One last one. So my colleague and I said Bangalore. I'm done. Gotta wake up people.
No, we didn't have any workshops on trees, right? We never had any workshop. No, it was not on trees, no? We never had. Not. Crops. Yeah, somehow, I had just one comment. Somehow I think in all the mathematics, the intuition is absolutely missing. When you say Brownian motion on a tree, somehow when a flat part, a straight line is there, it should be like usual Brownian motion. And you should only tell me when we reach a branch point, which branch you should go on. That intuition is missing. What data is telling you that? You know, new or? Huh. Oh, construction is based on that. I see. Right, I see. Right. Right, right, I see. I see. Right. So, yeah.
When you show it's a natural scale, you show that take a point x, take two other points a and b, translating u before a is exactly like point dimension.
But this, I mean, symmetric, the Dirichlet form is an abstract theory, which does not depend on a dimension or anything like that. So,
what you do is you get handle estimates on capacity and gain function from the Dirichlet form, and use that to get a heat kernel, and use that to get the
heat kernel is already there from the Dirichlet form.
Yes,
I mean, that.
for that you show that you show like measure is a crucial identity. No, what you're asking is, for example, like say there's an occupation measure identity that you have for diffusion or real life. You can establish the same thing on this particular metric space using your green function and capacity notions from the diffusion.
But how much information on the path can you get? That probably is what he has in mind.
Yeah, the path element is the following. It shows natural scale. So that means you take any two points, you pick a midpoint between them, you can go in natural scale, like the one that we did. And that tells you what happens at every branch. With every branch you form. You can, yeah. Not too hard, but it's abstraction. Correct. That's a problem with this. There's no hands-on part. It's an abstract thing. That's true in general.
Right. Okay, let us thank Shiva for the nice talk. So we shall meet after.